friends, I'm Ashish Darbari, founder and CEO of Maximize, and to our new listeners, you're very welcome. To our old ones, welcome back. I've got a real treat for you today. I'm extremely pleased to tell you that we have today in-house Lucio Lanza. Hi, Lucio.
Hi, Ashish. How are you?
Thank you very much. A person like Lucio doesn't need any introduction, so I dare not introduce him. Some of you who are new to the field might want to know he's actually been in the industry for 4 decades. He's a recipient of Phil Kaufman Award, and he runs his private company, Lanza Ventures, who's helping startups do innovative stuff. Thank you so much for actually taking the time to come and talk to us. Lucio, before we actually do deep dive, and it's sometimes difficult to decide when I talk to someone like you as to where do I actually start. But let me ask you a very simple question. Where did this all begin? Where were you born? How did you end up into science and engineering?
I'm glad you're asking where I was born, not when. I was born in Italy, and was the end of the war, 1944.
Oh, wow.
And I was born in Milan, Italy, in the center of the war and the bombing of Milan. So that was my starting point. And I studied in Italy. I went to middle school, but I went to, when I studied as a kid, I went to study classical studies. So somehow I love to study Greek and Latin and history and philosophy. Philosophy was probably the thing I liked the most. History of philosophy. In Italy those days, you don't study philosophy. You don't decide which philosopher to study. You study history of philosophy. You start with Egypt and you come to yesterday. That's it. You studied all the philosophers in the middle for the entire time, which makes you honest. You cannot really pick one area you really like.
That's right.
And I like the most. And but I also liked I like Greek and Latin. I like history. I also like this math and geometry and stuff. And when I finished high school, my at the class reunion, it was 10 people, 15 people. The class reunion, the teacher wanted to find out which college we would go to, and my philosophy teacher was very disappointed when I said I was going to go into engineering school. She felt like I was really a traitor, so I shouldn't do that. But I felt that engineering was a better way to get involved in society and have an impact on society. And I went to the Polytechnic of Milan. Polytechnic of Milan is a unique engineering school. It's a private school. And I remember when I went there at the time, and this was 1962, the number of kids that were in the first day that we went in class was 1,010 in one class.
Wow.
It was pretty big. And then during the engineering school, what we do, the first 2 years, we just study mathematical theory. That's it.
Right.
Okay?
Yeah.
It's all theory.
Yeah.
Then in the third year, you decide which area to go to, then you specialize more and more and more. So I moved from mathematical theory. I had to do. After the first 2 years, I moved to electrical engineering, and then various areas, then became on the electronic engineering. On the electronic engineering, only 25 people, if I remember correctly, were admitted. So I got to the electronics, and then 5 years and 2 months later, I got a degree in electronics. So that's
this is really fascinating. This is really fascinating because I live in Europe and I've been living here for 22 years now, and I know exactly. I can relate to what you're saying because I had lovely Italian teachers who were teaching me back in my Germany days when I was doing my master's. So I see that the passions run quite high when people are interested in pure maths or logic or philosophy. They really do believe in that. But I suppose one thing that philosophy teaches you is to think and always challenge the hypotheses and always ask to go more. It doesn't teaches you to be dogmatic, right? And I suppose in engineering and science, that kind of thinking helps you to grow out of your mold and challenge the status quo. And I think that's probably, you would have seen that would have helped you in engineering and science. But 1960...
That's a nice way to frame it. That's exactly the way I saw it. And I was very excited. At the end of the fifth year, I remember that this professor Italian professor that had been at Stanford for a couple of years, came there and had this discipline called computer science that he wanted to teach. He was teaching, and that was the only class that I was allowed to volunteer. Of the 30 classes that you had, 29 were fixed. That's it. You take those, and that's it. You have no choice. I remember I complained once to the head of the college, and I said, we should allow kids to pick ones. Pick. And he said, we're allowed to pick. Just tell you had 29 and you had to do. You can pick another thing. Okay, right.
But what's fascinating is in 1960s, if you were doing electronics back then, I mean, transistors had just about came. It was only about 5-6 years ago. This was just the era of vacuum tubes, and and to have actually started your career in that age, and here we are in 2020. In the age that we are, it's absolutely. You must have seen it all.
Transistors. I remember transistors. I remember because it was the days when you knew the transistor was a trans resistor.
That's right.
It was a resistor that would change. So fundamentally, that's a transistor. It's a resistor that can change.
Right.
It can change continuously. That's what I remember.
So, Lucio, is it right? Is it right to? So you did all of this back in Italy. And then you took up a job, if I'm not wrong, as soon as you finished your degree. You took up a career in electronics, right? But now you are doing network communications, satellite communications. I mean, how did that happen? Can you give us a brief overview of your 40-year path from graduating in electronics?
Making it brief may be difficult. But
I have time.
Because that was exactly 52 years.
Wow. Yeah. Yeah.
Because I finished in 67, December 67. My first job was in February 68, February 21, 1968. And that's when I joined the company called Olivetti.
Yep.
In fact, it was called at the time Olivetti General Electric.
Right.
It was the company that General Electric had just acquired the computers and done this subsidiary of GE called Olivetti General.
Right.
And they had a computer that was called the 115, TR-115, if I remember. It was just call it mini computer. A mini computer was as tall as me.
Right. This is 1967. You're saying, yeah, 1968.
That was 68 February when I joined. And I stayed there for some time until GE decided to take over the company completely. And then I had the choice whether to stay there or to join instead Olivetti.
Right.
Olivetti. So I moved to Olivetti proper, and now we're talking about 68, mid 68, end of 68. I joined Olivetti proper. And when I went to Olivetti, they started putting me in charge of connecting computers. Okay, so the first things I was doing, connecting computers. So via modems, to be precise. And I was designing the controllers for that.
Right.
And then designed those controller, and what was the name of the protocol? I don't remember this protocol. But then we decided to design some more complex things. And they thought, since I was so excited about designing controller, first of all, they moved me from Olivetti to Olivetti Milan. Olivetti Milan was a group of people in Olivetti that were in charge of moving back Olivetti into computers. So GE had acquired the computers, now was put back into computers. Mm-hmm. And I was there, I was living in Milan, and the office was a mile, 2 miles from where I was living. And was a team, at the time, it was a team 17 people, 18 people, that was doing just that. Mm-hmm. At this point, we had to design these things. And in that team, the first thing they asked me to do again is do a communication product, right. Which I did. And then they decided that they wanted to do a banking terminal. And they asked me to design a CPU.
Wow.
That's how I got into CPUs. And we're talking those days, now we're talking about 69, mm-hmm. Yeah, 69 and 70. And at that point, the industry was already having some SSI, small scale integral circuits, and some MSI, mid-scale integral circuits. The largest one that existed those days was a 4-bit shift register.
That's right. Okay? That's right.
93 amp to be precise. Outside 93. That was the one. And so I accepted the challenge to design the first computer for Olivetti. The first computer that became a computer. It was another one. And the gentleman that did that was the one who became the boss and asked me to do it. So we did that. And there was going to be a computer to be used in banking terminals. Because Olivetti was very strong in calculators.
Right.
And was owning the banking industry for calculators. And they just acquired Underwood in the States. So they wanted to have somebody that would design these things and make computer terminals. Okay? And so I designed that. And when I say I designed it, it looks very arrogant. Were two of us. And was one, the other one was Mr. Vecchio, VECCHIO. Mm-hmm. And he was very, very precise, great designer in depth. Mm-hmm. And so we designed this one. So that's how I ended up on the computer side. And when we did that, his computer became pretty successful. And now we're talking about really taking over, practically dominating the banking terminals in Europe. Mm-hmm. So they decided to ask me to find out how to make these terminals more and more powerful.
Right.
And there were companies in the States, they were doing things called semiconductors better. And Fairchild was one, mm-hmm. Motorola was another one. So fundamentally, we understood we could not design the processor ourselves. So mm-hmm. Because the only company in Europe, in Italy in particular, that could do that was called SGS Thompson.
Uh-huh. Yeah.
And SGS Thompson was not really advanced in the terminal technology. So they asked me, they put me in charge of going to the States and find out in the States which company was the right one to cooperate with and to work with. And I went to Fairchild and Motorola. And mm-hmm. Motorola was in Phoenix, the one for processors. And I went to National Semiconductor. I went to various companies. And at the end, I liked this small company, this smaller company that had just moved to Santa Clara. And I was in Santa Clara 1, the first building in Santa Clara. It was a small company called Intel.
Yeah.
And I liked them. I thought that they were very challenging, very intellectually challenging. So I went back to Italy and I advised the company, the Olivetti company, to work with Intel. It was my boss at the time was very, very, very smart. So it wasn't a fight. When I told him why, he understood, he agreed, great, let's do it. So we decided to establish a cooperation with Intel that happened to have a processor called 8080.
Mm-hmm. Right.
And they're just making the 8085. And the point is that as the designers of computers, the CPU was just a little thing. It wasn't the computer, it's just 1/10 of the computer. And what we wanted to do is convince Intel that they needed more than a processor.
Yeah.
If you want to support computer, they need more than processor. So they sent me there, and I worked with Intel, and we decided at Intel and I for Olivetti, we decided we're going to be working on other things. One was going to be a floppy disk controller called 8271.
Right.
Yeah,
right.
An SDLC controller called 8273. And the third was going to be a display controller called 8275.
Right.
So we're going to do the 8270X.
So this is mid-70s, right, Lucio? This is mid-70s.
We're talking about, early 70s, 72.
Yeah. Sure.
Like that. Yeah. 74. Yeah. No, 74. 74. It's 74. So, and we decided to do those. So I went back to Italy, and I could keep coming back from Italy to the States and working here and there. And at the end, I would say it was a pendulum, okay? But at the end, the pendulum got stuck in the States. I realized that at this point, I wasn't fitting in Olivetti as well as I was fitting in Intel.
Sure.
And that we're all going the same way, we're all going at the same speed, all challenging each other. It was very, very challenging place. And Olivetti wasn't as much. So I resigned from Olivetti, and I'll never forget it. They couldn't believe it that I would resign. It since they thought I was so successful in Olivetti, how can you resign?
Mm.
And I thought, don't tell me that I'm very successful, otherwise you're making me feel even worse. I'm leaving and you're telling that I shouldn't, you're getting everything. I don't know what to do. So I left and joined in the, so the one-way ticket was October 11, 1977. I moved to Intel for good.
Right.
And I was hired.
So that's a very exciting time, right? I mean, this is when processors were sort of going down because we had mainframes by that time and computers were like size of the rooms, and you were right there at the helm of it, talking to Intel about building processors, floppy disk controllers, all of the stuff that I have seen growing up as a child in India. And it's so fascinating. So Lucio, tell me this. So this was an exciting time. You were at Intel, one of the most well-known names now, and probably not as well-known as Fairchild at the time, and Motorola at the time, but how did you actually then move into communications then? What was happening in your mind about moving to communications, satellite communications, and that kind of direction?
Well, I think I really did not move into communications anymore. I think communication, after I joined Intel, I ended up staying in the processors, and ended up. That's a funny story. When I decided to leave Olivetti, I was in a position in Olivetti where I could not leave for 6 months. So I would resign, and I had to stay there by contract for 6 months.
Mm-hmm. Right.
So I stayed there for 6 months. In those 6 months, when I ended up coming back to Intel, I told Intel when I resigned, I'm going to be here in 6 months. They didn't believe me. I said, I have to stay there in 6 months. So when I came back after 6 months, Intel had decided to move and start designing a 16-bit processor.
Uh-huh.
They hired a guy from Western Digital down south, Bill Pullman. They would design this product. It was called the 8086.
Mm-hmm.
So when I joined in, they would design the 8086, but they still wanted to finish designing the other products. So the 75, 75, all the various controllers. So they wanted me to work on that. At the same time, they asked me to work on the processors. So at Intel, the first processor that was involved with was called the 186.
All right.
The 186 was an 86,
Mm-hmm.
but I wanted to do an integration of all the peripherals, so we could
Right. Mm-hmm.
of cost
Mm-hmm.
to be used for products.
Right.
Integrate all the peripherals.
Mm-hmm.
And so that was the 86. And then when I was there, I was doing the 186, and we started moving in the 286.
Right.
Okay?
Right. Right.
Almost in charge of the 286 initially. Then he left, ended up in charge of the 286.
So you're
So
talking about
that's-
you were talking about Phil Kaufman, is that right?
No, not yet.
Okay.
Phil wasn't there yet.
Okay.
The 286 was, I think, was Dave House at the time.
I see.
But I think, I don't remember exactly. No, Jean-Claude Cornet. Jean-Claude Cornet.
Okay.
So that's when the 286 was going. And the interesting thing on the 286 is that the 286 was a product that was looking at a CPU becoming more complex.
Mm-hmm.
Okay? Wasn't thinking as much about moving fast in technology
Right.
as becoming, in fact, instead of being a Unix machine, which is what I would have liked,
Mm.
was a multix machine. It was
Right.
a multiprocessor Unix. So that's why it was so complicated as an architecture. Very
Mm-hmm. Mm-hmm. Mm-hmm.
uselessly complicated.
Mm-hmm.
Okay? It wasn't really needed.
They need to be. Yeah, they need to be.
It didn't.
Mm.
So, but that was the 286, and then, and so that's where I got involved. So I kind of moved away from the peripherals, and they decided at Intel to put him in charge of the strategy, part-time.
Right.
That's when Intel decided to move into the strategic process. Okay?
Interesting.
The-
Mm-hmm.
the- and that was a huge decision for them. Still today, they have structure
Mm-hmm.
that they designed in 79.
Mm-hmm.
So that's same, identical.
Right.
It's called SPS, Strategic Business Segment.
Right.
And that
Right.
was put in charge of the strategy, the microprocessor SBS, Microprocessor Strategic Business Segment.
Mm-hmm.
Was the first person in charge of that. So that's what I did at Intel.
Cool.
And then at the same time, they started asking me to look also at the peripheral strategic business segment. So I kept moving in that direction and really was trying to understand how do we beat Motorola and the Motorola product. The 68000.
Mm-hmm.
The 68000 was really bothering us.
Right. Right. Right.
The way to do it was the 286 was more complex.
Mhm.
The 68000 was very nice, simple architecture. I really liked it. And the 286 was far more complex. So what we did is decided that we do that by making Intel do more around the 286, so
Mhm.
more
Mhm.
complex. And that's when we ended up doing stuff like, I'll go quickly, more quickly. We decided, for example, that connecting computers via SDLC or HDLC made no sense. You're going through telephone lines.
Right,
Telephone
right.
lines don't move as fast as the computer. So we decided we need to connect computer to computers. How do we do that? How do you do that? Well, how do you do that? Well, that was my first design when I went to Olivetti General Electric was doing that. So I asked some friends of mine at Olivetti, what is good today to connect these things? And one friend of mine there, Mario Mazzola, told me, there is a connection that a research organization called Xerox PARC, and it's a good one. It's a good connection. And I really liked Mario Mazzola. Was a technical guy, very good. Was working with me at Olivetti. And I brought him into Olivetti here, myself, and here in the States. And they said, yeah, well, let's look. Let's see if we can get this thing going. So we talked to Xerox PARC, and now Kaufman was on now. Kaufman was now the CEO, the general manager of the microprocessor. So Kaufman and I talked to Xerox, and Xerox said, okay, if you want to use this, okay, we'll let you do it. But then we decided that in order to make this a standard, we needed a system company
Mm-hmm.
computer company to do that.
Right.
And of course, which computer company we got? Olivetti. So we went to Olivetti to ask them whether they would in fact become part of this three-ways team that
Sure.
will make this a standard. And Olivetti, the guy at Olivetti in Italy, said absolutely not, because he was in a different division of Mario Mazzola, so he didn't want to favor him. So
Sure.
at the end, Olivetti said, "Oh, we don't do it." So we left, and when we came here, I remember Phil Kaufman and I were sitting down, and Phil says, "So what are we going to do with Olivetti?" I said, Olivetti who? There's no Olivetti in my life. What are we going to do for this? I said, well, we need another system company. And we said, what about digital equipment? And we said, let's call digital. And so we called it, and the name of the guy came in. And he said, we do have a .NET, but I like the internet. I think I really like what Xerox has defined. So we decided, okay, we're gonna go and do exactly that.
Mm-hmm.
So the three-way thing happened, and then we decided to do the Ethernet. The first Ethernet controller was done exactly that way.
Yeah,
So
I know. I read about it, and I really wanted to hear it from you today, and that's why I wasn't meaning I wasn't meaning to give you a hard time trying to stretch your memory, but I wanted you to share this history with us, because I've read this somewhere about how the Ethernet protocol came and how you were involved at the time. So thank you very much for sharing this. Let me move on, Lucio, because I want to talk to you about what you're doing these days. So what are you up to these days? I hear you have a keen interest in medical electronics and health electronics. Tell us about what is happening now.
You see, let me tell you, at this point, when I see that the semiconductor industry second derivative of growth has changed from positive to negative. So you have the second derivative that is just barely there. And the first derivative is slightly positive, but the second is negative. So it's just going this way. And when it's going this way, you have to look at which applications are moving in an exponential way with strong second derivative. And of course, the computing power and the computing power itself, the computers themselves they're not moving that way. But if you look at the other areas where the demand is growing exponentially, it's naturally exponential. Okay, if you look at the healthcare and you look at the drug discovery process, drug discovery process, guess what? Is a negative second derivative.
That's right.
It's just you spend more money to discover a drug than you're going to make with the drug. So ain't it a good business? So somehow you look at that and you say, okay, but is the demand for drug discovery, is the demand for new drugs positive? Is the second derivative demand positive? Of course it is. It's unbelievably positive.
Yeah.
So what we need to think is, how do we apply technology to address that exploding demand?
So you're focusing specifically on drug discovery, is that right? Not on wearable health, which is the market, for example, with the watches and sensors.
I'm focusing on both.
Both, I see.
I'll tell you, drug discovery is one with technology. The other thing where things are growing exponentially is what I call IoT. The Internet of Things, the number of things they want to connect it and become, I call them citizens of the Internet, is exponential. So you have to have these things coming in. And they don't come in naturally because the Internet is digital, and so happens the phenomena are analog. So you need to have something that gets analog into digital, and you need to have an entire industry goes in that direction. So from that point of view, you need to have the ability of making these designs unbelievably cheap.
So, Lucio, this is a very competitive market with the big vendors, like the likes of Apple and Google and Samsung and whatnot. I mean, you're batting for some small companies in this segment. Am I right or wrong?
Yes. But let me give you an example. Yeah, I look at small companies. So would Apple say, okay, I'm going to bring in all the good ideas that some guy in Ukraine has? No. I'm going to send good ideas that somebody in Tanzania has? No. Okay. How do you get those good ideas here? Well, you have to think differently.
Mm-hmm.
And there's a company that happened to be involved when we started it. And we said, okay, if you want all these IoTs coming in, you have to understand that analog designers are a different generation of people, different minds.
Correct.
They're not digital like me.
That's right.
They're very creative. They don't want to drive 2 hours to go to work, and they want to leave their home or the country they're in to go and work in Silicon Valley. Don't do that.
Right.
So you need to be there. So how do you do that? Well, you have to create a network, and you make a network of analog designers.
Mm-hmm.
That's one thing that we started.
Right.
So
I see.
how do you do that?
Yeah.
You post a spec on the network.
Mm-hmm.
You post a spec on the net,
mm-hmm.
on the internet. Say, hey, would you please bid on this design?
Mm-hmm.
And you know what happens? You get 80 bids. And you look at that, you go, wow, this is a good one. This is good. Oh, great. So, yeah, it is. So now your technical problem is being solved.
Mm-hmm.
You could never be able to solve it, to go find out who exactly knows how to do it. But you created a natural way
mm-hmm.
of bringing designs in.
Right.
Now the design is in, and the analog is in. Now you need to do the rest of the design. How
right.
do you do that? Well, the way to do that, probably the people trying to do the designs are not large companies. So, 5 kids in the garage.
Mm-hmm.
So how do they do that? Well, they cannot pay much for design tools.
Mm-hmm.
So you need free design tools. Okay, open source design tools. Push for open source.
Right.
So same company decided
right.
after having the
sure.
design coming in
yeah.
to open source tools. So I think that is very important to bring in more ideas.
So you're a big supporter. You're a big supporter of open source tools because for the reasons that you're describing, and I totally agree with you. Yeah, I think to drive innovation more freely, that's the way to go. It's a very interesting point you made about analog and how digital and analog are not. Sometimes I see them as being tangential to each other, but without the analog, we can't get the digital to work, and it's in both ways, right? So we need processing backend on digital, but the real world is analog, right? So.
I remember when I did this thing, announced this thing, this analog design network. I remember that a good friend of mine, very smart guy, he was working, I don't know which company, a very important company, very strong in analog in Italy.
Sure.
Called me and said, "You son of a bitch, you realize that every engineer in my company will work for you at night."
Yeah, that's right. That's right.
Yes, I do.
But it's a very simple idea if you think of it, what you actually seeded, which is to bring the whole community of analog designers on the same platform and get the best ideas to form an ecosystem effectively. That's what you're saying you've done.
Absolutely.
So how far along, how is it going? I mean, where are you in that stage?
This company is there. Now, as also the digital portion,
right.
So as open source thing,
okay,
is you see, as the open source thing now, but looks at open source not as replacing other tools, not replace the standard tools. No, the point is the open source things that will be very successful will need to be more complex and will become new customers for the standard way of design.
Sure.
Okay? And you increase the community of designers and you multiply by a factor of 100, the existing set of tools will succeed because of those 100, 2, 3, 4, 5, 10 will be successful. So the entire market is growing. You just extend it. To me, the only other example of this is when we move from just custom ICs to semi-custom ICs. Was the number of IC designers going down? No, went up like crazy. Was the number of electronics going down? No.
So this is,
when
what is...
Into the community, you get everybody.
What is really striking my mind right now, knowing your history with Cadence before, and you were also at ARM as a director, and now here you are saying, look, to drive innovation, we need to support the open source ecosystem and drive it in that way. This is very nice to see that you have that kind of perspective on the industry, because these EDA tools that are being sold in the market are they've gone through so much design and stability phase, and they're very good in quality, and it's taken them a lot of time to make these. And I think what you're saying is, with open source, with the diversity of ideas and how people communicate more effectively in an open spirit, and Linux is a classic example of how we have such a beautiful operating system. Absolutely. So Lucio, what else? I mean, I wanted to actually just ask you this. We are living in 2020 with 5G driving a lot of innovation, IoT, as you mentioned, and artificial intelligence. Every single day you hear something or the other. Where do you see us going in the next decade or so with the convergence of these technologies in the hardware space, especially impacting automotive? What are your thoughts on this? Are we going in the right direction or the wrong direction?
I'll tell you a couple of places. One is, what is going to happen is that we're going to have an explosion of the AI and machine learning devices. And that is going to require so much computing power, so much creativity that we've never seen it before.
Right.
It's also a different kind of creativity. And when you're mentioning about medical, to me, medical is an area where that specific approach would change the industry completely.
Right.
Because you're going to have machine learning, and the beauty of machine learning and this computer is that when you think that the thing is flat, it's not sequential. It's not like human beings. Okay, I'm going to do this, do that. Yeah. My brain is not big enough to keep a big my mind. Yeah. So you keep optimizing too soon. The industry, the way the medical and the pharmaceutical industry have been going, sorry, I don't mean to be negative, fantastic stuff, it might be politically incorrect, but it's been optimizing serially. So they do the entire process serially. And when you do that, it's difficult. It's difficult to have completely innovative and creative ideas.
Right.
If you go with open AI machine, you can look at more data than you could ever be able to look at the same time.
Yeah.
And so that is where when I talk about totally changing the healthcare industry, that's what I'm thinking. I'm thinking at looking at. Sometimes I do this, and I used to do that part. Assume you have infinite computing power. Of course, it's impossible. Assume you have infinite computing power.
Yeah.
What would you do if you want to do a fantastic medical technology and medical power? Infinite computing power.
Right.
I'm going to take computing power. I'm going to take your DNA. I'm going to ask my computing power, will you please tell me, for this DNA, for this person, for this thing, what is the thing that is wrong, and why is it more prone to have Alzheimer? Okay?
Yeah. So diagnostics. Yeah.
So if you have infinite computing power, the diagnosis become precise. And
that's right.
Individual.
That's right.
You.
That's right.
Your DNA.
That's right.
Now, of course, it's not infinite, but you can see that the trend is that direction. The trend is not in making more and more people, making this good for everybody. No, the trend is making it good for that specific disease, for that specific variation of Alzheimer.
That's right.
Not for every Alzheimer you can see. There are 20 different ones. So,
yeah, sure.
So that's the way I'm looking at the way things are going to evolve. Okay.
No, that's quite correct. And actually, if you throw in 5G into this, and if you think the machine-to-machine connectivity could be accelerated, then data could be passed around, the diagnostics could be done off-site. They don't have to be done right at the node where you're sampling the data. So you can actually then get the best of. So you're giving an optimism view to me right now. So you're saying we're going to be getting better and better at addressing health diagnostics.
Absolutely.
Yeah. And this is a very positive thing
to see young people to concentrate, look at. They have to look at what is that can be done.
Right.
Now, as I always say, assume infinite computing power. Tell me what you can do.
What you can do.
And this at Intel, we used to do that. Always we say, the objective is something that is not achievable. You can see that's the objective. Okay? Now do a real clear decision on what you're going to do in the next month.
Correct.
Okay?
Correct.
Now,
correct.
Something clear, measurable. Okay? That's what we organize the entire processing of planning with Intel. You get something very nice as an objective, and then you get which steps you can make.
So this is so apt, Lucio, just in the modern time, the year 2020, we are going through this pandemic. And the whole society as a whole has never been well prepared for such pandemics. And what you're saying is that what you're looking at and what kind of projects you're supporting at some point, we could imagine living in a world where we have this supposedly infinite compute power, which is then formed into this advanced diagnostics, and we could then get after these pandemics ahead of them, right? So we could potentially stay ahead of these things, not just the more chronic Alzheimer's or the cancers, and of course they're all quite bad, but this is going to be quite a big concern from what I hear going forward, with the pandemics becoming more and more frequent.
Take this pandemic. It's obvious what the limitations are.
Mm-hmm.
In this pandemic, the real limitation that you have here is a limitation because of a structure in the medical system that is a little obsolete.
Mm-hmm.
You need to have constant contact.
Yeah.
Okay?
Mm-hmm.
The idea that you have an episodic contact with your health provider doesn't make any sense. It should be continuous.
Right.
Okay?
Right.
The contact should be continuous. You should have a constant interaction. Okay? In fact, not even your device, the one that is really taking care of your little disease and informing the doctor of your disease, should be connected to the doctor continuously. Period. Okay? And if you have somebody in a senior home, he should be connected, he or she should be connected to whoever is knowledgeable about their need, whether their physical health need or emotional needs, continuously. There is no reason not to have a continuous connection. None. Okay? Connection is feasible today. Okay? And one of the results of this pandemic will accelerate the connection, accelerate the continuous connection, and stop thinking things have to be episodic. They are not episodic. The second you stop thinking of healthcare as episodic, you find out that the healthcare becomes not medical care, but healthcare.
Healthcare.
That means you're taking care of your health, not your disease.
Correct.
That's the difference. Okay?
Correct. 24/7 online monitoring and advanced predictions. That's what you are basically saying. That's the world you are envisioning going forwards. Really, really nice.
That's the way it's going to be. There's no reason for you to get sick. Don't get sick. Just don't do that. Your body doesn't want it. Please don't do it. That's the way you don't get sick. Okay.
So Lucio, I was just looking at the clock and I was saying, oh, we've already been talking for the last 40 minutes or so. So I know you have a lot of things to look at. So I don't want to take too much of your time. But before we wrap up for today, I wanted to ask you, for someone who has spent this long in the industry, what would be 5 tips if you wanted to give it to young people today, starting a career in electronics or software? What would be your 5 recommendations?
The first thing I would say today, get familiar with computers. Very familiar.
Okay, yeah, that's a good one.
Second one, get familiar with AI.
Sure.
Okay?
Yeah.
And machine AI. Don't think like a computer. A computer is a sequential machine. Ping, 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 ping. Don't do that.
Yeah.
Okay?
Yeah.
Open your mind. Look at the big thing. Look at the big picture. Try to see how things are connected with each other.
Sure.
Okay? And just don't assume that the past is what it is.
Mm-hmm.
Look at the evolution of things.
Mm-hmm.
One evolution, for example, you have to think about.
Mm-hmm.
Distance is dead.
Right.
Okay? Doesn't exist anymore. I
Sure.
don't know where you are.
Sure.
Doesn't matter.
Sure.
Okay?
Yeah.
Distance was given a death pill when we started Italy. Okay?
That's right.
Now it's not.
That's right. That's right.
Distance is not meaningful anymore.
That's right.
Okay?
That's right.
That's so. Look at that. Don't think about distance. That's and so just what I call is just think flat. Okay? Don't think sequential. Okay? And that is something that will allow you to understand in the way society is doing things, not necessarily to insert yourself and improve a little step.
Sure, right.
Okay?
Right.
That's and then once you do that, then you go back to the being process oriented, because your brain ain't the flat.
Sure.
And you say, okay, what is the objective I have here?
Sure.
This is the objective. If that's the objective, what is the result I can achieve in a reasonable time?
Right.
That's it. Those are my three things.
That's awesome. This is really nice. I like this thing that you said, think flat and don't think sequentially. So as if almost like you broaden your opportunities of growth and where you can go. And then once you've identified which ones you want to go after, then you put a structure and a process behind to chase them. That's what you're saying.
Exactly.
Wonderful. And really coming from you, it just means a lot. And thank you so much for coming and talking to us today, Lucio. I know you are a very, very busy person, and I'm deeply grateful to you. Deeply grateful to you for taking the time out. Thank you very much.
Thank you. Take care. Bye now.
Thank you. Bye. So friends, I hope you enjoyed today's chat with Lucio. It's not very easy to find people like Lucio. And I hope you stay in touch with us and do let us know if you enjoyed today's podcast. Do let us know by info@aximize, by emailing us at info@aximize.com and sharing your thoughts on our YouTube channel. Stay healthy and we will be back again. Thank you very much.